Okay, 2023 released FRQs for the AP Statistics exam. I'm going to work number 6, and again, working these cold so that I have nothing except for what students have available to them on the exam as I'm working them. Haven't looked at this before, total sent a few comments about it, but nothing to really give it away. So a jewelry company uses a machine to apply a coating of gold on a certain style of necklace. The amount of gold applied to the necklace is approximately normally distributed. When the machine is working properly, the amount of gold applied to a necklace has a mean of 300 milligrams and standard deviation of 5 milligrams. Part A, a necklace. Let's go ahead and put this up here. Part A, a necklace is randomly selected from the necklaces produced by a machine, assuming that the machine is working properly. Calculate the probability that the amount of gold applied to the necklace is between 296 milligrams and 304 milligrams. So, 2023, AP Stat, FRQs, number 6A. And this we said was approximately normal, so I'm going to sketch the curve with a mean of 300 milligrams and standard deviation of 5 milligrams. And we're interested in the probability between 296 and 304. So we're looking for the probability that 296 is less than or equal to x, it's less than or equal to 304 milligrams. And that's going to be equal to, we're going to use the calculator. And we're going to do normal CDF. Oops, so it's already on the calculator. We're going to go to 296. And the upper bound is 304. And the mean is 300. And the standard deviation is 5. I'm going to go ahead and enter that in the calculator syntax. So I'm going to do the normal CDF, where the lower bound is 296. The upper bound is 304. Mean is 300. And standard deviation is 5. And we're going to calculate that. And we get 57.6%, or 0.576. That's the probability. So I'm going to go ahead and write this in context. And if the machine is working correctly, the probability of the amount of gold is between 296 and 304 milligrams is 0.576. Okay, let's go to part B. The jewelry company wants to make sure the machine is working properly, so each day Cleo, a statistician at the jewelry company, will take a random sample of the necklaces produced that day. Each selected necklace will be melted down, and the amount of gold applied to the necklace will be determined. Because the necklace must be destroyed to determine the amount of gold that was applied, and Cleo will use random samples of size n equals 2. Necklaces. Cleo starts by considering the mean amount of gold being applied to the necklaces. After Cleo takes a random sample of n equals 2 necklaces, she computes the sample mean amount of gold applied to the 2 necklaces. So it looks like we're looking for sampling distribution with n equal 2, which is not a worry because we're coming from an approximately normal distribution. Suppose the machine is working properly with a population mean amount of gold being applied of 300 milligrams and population standard deviation of 5 milligrams. Calculate the probability that the sample mean amount of gold applied to a random sample of n equals 2 necklaces will be greater than 303 milligrams. Okay, so this time Our X bar is the sample mean for N equals 2, amount of gold, for N equals 2. And this time we're going to draw the sampling distribution. So the mean of X bar will be equal to the mean of the population, and the standard deviation is going to be equal to the population standard deviation of 5 divided by the square root of N, which is the square root of 2. So we're looking for the probability that the sample mean X bar is greater than or equal to 303, or greater than, strictly greater than it says here. So I'm just going to go greater than. Same probability because it's a continuous distribution, but we're going to go strictly greater than 303 milligrams. And so this time we're going to use a different standard deviation. We're still going to use normal CDF and do second distribution, normal CDF. And this time we're going to do the lower is 303, and I'm going to use infinity here on the calculator. Highest number the calculator can take, 10 to the 99th power. The mean is 300, and this time the sampling standard deviation of the sample distribution is 5 divided by the square root of 2. I'm going to go ahead and write that in here. Remember, if you use calculator syntax, you have to label everything. Lower bound is 303, and the upper bound is 10 to the 99th. And the mean just simulates infinity on the calculator. It's 300, and the standard deviation is 5 divided by the square root of 2. And that probability is 0.198, or 19.8%. So let's just go with that with the I. We won't write out a sentence for that. That's pretty clear. Suppose Cleo took a random sample of N equals 2 necklaces that resulted in a sample mean amount of gold applied of 303 milligrams. Would the result indicate the population mean amount of gold being applied by the machine is different from 300 milligrams? Justify your answer without performing an inference procedure. Okay, so we have X bar equal to 303. We've already set it greater than 303 as a 19.8% probability. And so I'm just going to say the probability of getting a sample mean as extreme or more extreme than 303 milligrams if the machine is working correctly is 19.8%. So I would not consider this compelling statistical evidence. It's actually not 19.8, it would be 39.6, because we'd be looking at a two-tailed test because it says not equal to. So I'm going to change that to 39.6% because 0.198 times 2 is 0.396. I would not consider this compelling statistical evidence to show the machine is working incorrectly, or the amount of gold. So, amount of gold, we'll put it in context of the problem, is different than 300 milligrams. I'm not sure if that's what they wanted, but that's what I'm going to do for this number 6, part B2. Okay, now Cleo will consider the variation in the amount of gold the machine applies to necklaces. Because of small sample size, n equals 2, Cleo will use the sample range of the data for the 2 randomly selected necklaces rather than the sample standard deviation. So the difference between the 2 samples, between the 2 necklaces in the sample. Cleo will investigate the behavior of the range for samples of size n equal 2. She will simulate the sampling distribution of the range of the amount of gold applied to 2 randomly sampled necklaces. Cleo generates 100,000 random samples of size n equals 2, independent values from a normal distribution with mean 300 and standard deviation 5. Range is calculated for the 2 observations of each sample. The simulated sampling distribution of the range is shown in graph 1. This process is repeated using standard deviation equals 8, as shown in graph 2, and again using standard deviation equals 12, as shown in graph 3. Use the information in the graphs to complete the following. For part C, I'm going to use another page. Describe the sampling distribution of the sample range for random samples of size n equals 2 from a normal distribution with standard deviation equals 5, as shown in graph 1. Okay, so the distribution of sample ranges for samples size n equals 2 of the gold in the necklaces is right skewed. We're going to say the median, let's see, this is about 11%. So altogether, this is going to make about 32% here, and then about 42%. So this is a little more than 8. So it looks like the median is, let's see, 1, 2, 3, 4, 5, 6, 7, 9, 10. So it looks like the median is about 5, with median approximately 5 milligrams. And the interquartile range, the 25th percentile would go into the 0.03 band. So Q1 would equal 0.03, and Q3, let's go to 75, so that's going to be, we said 50, about 50%, let's say there, and so another 8, and 7 is 15, and 6 is 21, and more than 5 would be another, so it's about 76. So I'm going to say Q3 is approximately, let's do this again. All right, so let's just calculate this. 0.11 plus point, let's say 108 plus 0.105 plus 0.95 plus about 0.09. Let's go ahead and add those up. 0.11 plus 0.108 plus 0.105 plus 0.095 plus 0.09. And that took us over 50%. That is at 0.05. So this is 0.508, and this one is 0.05. Median, or range, equals 0.05. So I'm going to keep adding until we get to the 75th. Let's see, 1, 2, 3, 4, 5, and then 0.08 plus about 0.07, let's say 2, plus 0.06, that's 0.21 something, and the next one is going to be about 0.05. And so if we add those up, 0.08 plus 0.072 plus 0.06 plus 0.05, it's about 26.2. So that's going to take us into the past the 75th percentile. So this is 0.262. So Q3 is equal to this was 0.05, 0.06, 0.07, 0.08, 0.09. So I'm going to say with interquartile range, 0.09 milligrams. We got right skewed, center, 0.09. The interquartile range is 6 milligrams, 0.06 milligrams. IQR, let's go ahead and show our work there, equals 0.09 minus 0.03. So 1.5 times that would be 0.09. So we would have to add 9% to 9 to get to 0.18. And it looks like we're going to have somewhere in the neighborhood of, with approximately 1% of the median or the ranges greater than 0.18, which would be outliers. Okay, that's the distribution, the description of that distribution. Describe how the sampling distribution of a sample range for sample size n equal 2 changes as the value of the population standard deviation increases. Okay, So we can see that the range of the distribution of ranges increases. Well, I think we'll see one. The range of the distribution of ranges increases approximately 22 milligrams for sample standard deviation. The standard deviation of that distribution, or the population standard deviation 5, and approximately 33 milligrams for the population standard deviation equal 8, and approximately 45 milligrams for the standard deviation equal 12. The medians, therefore, get larger as the standard deviation increases. If we did this would be 1, 2, 3, 4, 5, 6, 7, 8, 9. So somewhere around 8. So we said the median was 5 milligrams with standard deviation equal 5, approximately 8 milligrams with standard deviation equal 8, and approximately so here we have 4. So for average about 4. 1, 2, 3, 4, 5, 6, 7. Above 4. 1, 2, 3, 4, 5, 6. Going a little bit lower. 7. Below 4. So that's about 15 times 4. That'd be about 60%. So we're looking somewhere in the neighborhood of 12. Again, approximately 12 milligrams with standard deviation equal 12. The distributions of ranges becomes more strongly skewed right as the standard deviation increases. We're going to let that suffice for now. Recall that Clio needs to consider both the mean and standard deviation of the amount of gold applied to the necklaces to determine whether the machine is working properly. Suppose that 1 month later, Clio is again checking the machine to make sure it's working properly, and Clio takes a random sample of 2 necklaces, calculates the mean amount of gold applied as 303 milligrams, and the sample range as 10 milligrams. Recall that the machine is working properly if the amount of gold applied to the necklaces has a mean of 300 milligrams and a standard deviation of 5 milligrams. Consider Cleo's range of 10 milligrams from sample of size n equals 2. If the machine is working properly with a standard deviation of 5 milligrams, is the sample range of 10 milligrams unusual? Justify your answer. So if we go back to the 5 milligrams in the simulated ranges, and we said 10, is that right? The range was 10? Yes. If we go back to the diagram, 10 milligrams would put us at a little less than 4, about 3, so we're about 7%. So let's see here. The probability, let's go D, the probability of sample range greater than or equal to 10 milligrams is approximately, let's go ahead and say 0.04 plus 0.03 plus 0.025 plus 0.02 plus 0.015 plus 0.01 plus 0.05 plus 0.01. So I'm just going to say plus about 0.015 for all those last three. So that's going to be 7, 9.5, 11.5, 12, 13, 14, 15.5, which equals 0.155. So I would say we expect approximately 15.5% of the sample ranges to be greater than or equal to 10. So I would not consider a sample range of 10 to be evidence the machine is working improperly. Let's make sure we answer that question the way they asked it. I would not consider to be evidence the range of 10 milligrams is unusual when compared with reasonable values of alpha for hypothesis testing. Let's go to the second part. Do Cleo's sample mean of 303 milligrams and range of 10 milligrams indicate the machine is not working properly? Oh, I think we've probably just answered that. I think we've probably just answered that. We look at these as independent samples. Sample 1 and sample 2, 10 milligrams. I think that the last part of that. So I'll consider a sample range of 10 to be, how about just unusual. And then we'll take this and we'll put it in part 2. No. Both the probability that the sample mean is greater than or equal to 303 and, or let's do not equal to, the probability that the sample range is greater than or equal to 10, are both larger than any normally acceptable p-value such as 0.01, 0.05, or 0.10. Therefore, an inference procedure with hypothesis H0 as the machine is working properly would not be rejected since we have insufficient evidence. And I'm going to call that my solution to number 6. Let's see here. Stop.